Hey everybody, welcome back to Unit 3. We're going to take a look at Module 2. In this module, we'll discuss covalent bonding and we'll also learn how to draw some Lewis dot structures. At the beginning of last module, we talked about the comparison between ionic bonding and covalent bonding and metallic bonding. So let's review some of the key concepts of covalent bonding. First of all, covalent bonding happens between nonmetals bonded to other nonmetals. So this is not ionic bonding. Ionic bonding happens between metals and nonmetals. In covalent bonding, nonmetals bond to other nonmetals. So with that being said, there are very limited options as far as the elements that are participating in covalent bonding. Most often, you'll see things like carbon, oxygen, nitrogen, hydrogen, and all of the other elements in the upper right-hand side of the periodic table, excluding the noble gases, because as we know, noble gases don't bond to anything. Now, the mechanism of covalent bonding is that instead of forming ions that attract each other, like in ionic bonding, covalent bonding, electrons are shared between both of the nonmetals. Let's take, for example, say fluorine. Fluorine has 7 valence electrons in its highest energy level. And there's another fluorine with 7 valence electrons in its highest energy level. Now, this fluorine on the left is going to want to take an electron from the other fluorine, but that would leave the fluorine on the right now with 2 electrons away from a full energy level. And that doesn't help the fluorine on the right. The fluorine on the right's like, hey, give me 2 electrons. I want to have full valence energy level. And then the fluorine on the left is going to have 2 short. So what they do is they get together close to each other and they share an electron between the 2 of them. Each sharing an electron. What results then is a covalent bond. Covalent bonds happen when the valence energy levels overlap one another and they begin to share their electrons. So this one on the left now has 8 valence electrons if it shares 1 from the fluorine on the right. And this fluorine on the right has 8 valence electrons because it's sharing from the fluorine on the left. And covalent bonding happens in this way where there's a sharing of electrons. In my last example with fluorine, when both fluorines shared 1 pair of electrons between the 2 of them, we call that a single covalent bond. But some elements might want to share 2 pairs of electrons with each other. In that case, every pair of electrons they share adds another covalent bond between them. So 2 pairs of electrons shared is a double covalent bond, and 3 pairs of electrons, which is rare but happens, is called a triple covalent bond. Examples of molecules that double bond are oxygen bonded to other oxygen. Each oxygen has 6 valence electrons. Each oxygen wants 2 more from its neighbor, and so they share 2 sets of electrons, or 4 total electrons, with each other to create a double covalent bond. And an example of a triple covalent bond is nitrogen, N2. Nitrogen gas, the gas we breathe, 70% of our atmosphere is nitrogen gas, and that nitrogen gas is triple bonded to itself. Nitrogen triple bonds to nitrogen because they want to have 8 valence electrons in their highest energy level, and the only way to do that is to share 3 sets of electrons between each other to create 8 for both nitrogens to become stable. Now, when we show covalent bonds, usually what we do is we take the 2 electrons and we connect them, and so I showed the dot connecting to the X. This is a pair of electrons that is representing a bond, a covalent bond. If you look at the fluorine on the left, I draw a circle around all the electrons it has access to, and it's 8, 2, 4, 6, and the bond now counts as 8. And the fluorine with the X's has 2, 4, 6, and the bond also has access to 8. So we show a covalent bond as a line connecting 2 electrons. Now in a double bond, we would have 2 lines connecting 2 pairs of electrons. But once again, if you count the electrons that the oxygen on the left has access to, it's 2, 4, and now it's sharing 2 pairs of electrons for 8. Finally, for the triple covalent bond, as you'd expect, since it's sharing 3 pairs of electrons, we show that as 3 straight lines connecting these nitrogens. But the nitrogen on the left has access to 2 electrons of its own and 6 in the middle, making 8, and this nitrogen has access to 2 on its own, and then the 6 in the middle to make 8. So I draw these circles to show the electrons that each nitrogen has access to, and the ones in the middle are the covalently bonded ones, as you can see, representing a single, a double, and a triple covalent bond. Going back to my last example of fluorine bonded to fluorine and the two electrons that are being shared in between the two fluorines. Both of these fluorines are trying to pull the pair of electrons away from the other fluorine. This one on the right is pulling the electrons towards it, and this one on the left is trying to pull the electrons towards it. And we draw arrows to show the movement of the electrons. But since these are both pulling equally but in opposite directions, they cancel each other out. And so really not one fluorine is pulling the electrons closer to it than the other fluorine because they have equal strength or equal pull. This is what is known as a nonpolar covalent bond, where the electrons are shared completely equally. Both elements are pulling equally on the shared electrons. So they are sharing them equally, nonpolar covalent bond. But what happens if, for example, instead of a fluorine bonded to a fluorine, I have a fluorine bonded to a hydrogen? Now, fluorine bonded to hydrogen will create a covalent bond. These are two nonmetals. These electrons are going to be shared, but fluorine is pulling on the electrons much more strongly than the hydrogen is. The fluorine has more pull, and so this is what is referred to as a polar covalent bond, where the two elements are sharing electrons, but unequally. There's a measure of strength that each element is pulling on the electrons with, which is something that we're going to talk about on the next slide. But the point is, if ever there's a situation where the elements are pulling on shared electrons unequally, it is called a polar covalent bond. These are two vocabulary words, so make sure you know the difference between a nonpolar covalent bond and a polar covalent bond. Electronegativity is a big long word that means basically the strength at which an element is pulling on bonded electrons. An electronegativity value tells you how strongly the electrons are being shared between two elements. If you look at this periodic table down here on the screen, you'll see that instead of atomic masses, there are values that represent the strength or the electronegativity. What you'll notice is that the green are things that have low electronegativity, and the red are things that have high electronegativity. And generally speaking, electronegativity increases as you move from left to right along a period. Also, electronegativity increases as you move from bottom to top. So if you remember from our unit on periodic trends, the smallest elements are located in the upper right-hand corner. These happen to also mean that these small elements have high electronegativity. The smaller the element is, the more strongly it attracts bonded electrons. Electronegativity is a unitless value that is used to measure strength of pull on bonded electrons. And you will be given and have access to a periodic table of electronegativities in order to help you calculate the polarity of a bond. So how do we use electronegativity to calculate the bond polarity, or in other words, the pull on the bonded electrons? Well, it's pretty simple. All you need to do is take the two elements that are in question, or in other words, the two elements that are bonded to each other, and find their electronegativity values. If you take the electronegativity value of element 1 and subtract the electronegativity value of element 2, you get the bond polarity. Sometimes that number is a negative number, and sometimes that number is a positive number. So I always say subtract the bigger number minus the smaller number, or always think about taking the absolute value. Bond polarity is always a positive value, so just take the absolute value, and you've got the bond polarity. Let's say, for example, you've got the molecule CH4. C is in the middle, and it's bonded covalently to hydrogen on 4 different spots. Now let's take a look at the bond polarity of just one of the CH bonds. Well, C has an electronegativity, based on our electronegativity periodic table, of about 2.6. And hydrogen has an electronegativity value of about 2.2. And if I take the electronegativity value of the bigger one minus the smaller one, I have a difference of about 0.4. Now what does that mean? Well, the bond polarity falls upon a continuum where down here on the left, a 0 difference in electronegativity is nonpolar, and over here on the right, a electronegativity difference of anything less than 2.0 is considered polar covalent. Every once in a while, you'll get a difference in electronegativity that is greater than 2.1, but that's pretty rare. But if it happens, we typically call that an ionic bond. Think of this. In an ionic bond, one element is pulling on the electron so much that it completely removes the electron from the other element. Well, that is, by definition, a transfer of electrons and an ionic bond. But typically we use electronegativity values to judge the strength or polarity of a covalent bond. Now, anything less than 0.5 is technically considered nonpolar. Even though it might be a small difference like 0.01 or 0.02 or 0.03, we call this a nonpolar covalent. So in the example that I just did, a difference of 0.4 would be considered a nonpolar covalent bond. But anything greater than 0.5 up until about 2.0 is considered a polar covalent bond. And anything greater than a difference of 2.0, as we talked about, is ionic. So this is the last thing that we're going to do in this video lesson. We're going to calculate the bond polarity of the following covalent bonds and then indicate if this bond is polar or nonpolar, or in some cases, very rare, ionic. Let's first start with this C-Cl bond in the Cl4 molecule. Well, we find the electronegativity values, and once again, you would have access to an electronegativity periodic table, but I'm just going to write them in for us today. This one is 2.6, and chlorine has an electronegativity of about 3.2. So if we take the difference in electronegativity between these two, we take 3.2, subtract 2.6, or take 2.6 minus 3.2, and then take the absolute value. What we get is a difference of about 0.6. Since that is greater than 0.5, this is a polar covalent bond. The next one is silicon and hydrogen in the molecule SiH4. Well, silicon has an electronegativity value of 1.9, and hydrogen is an electronegativity of 2.2. Now, when we subtract those and take the absolute value, we have a difference of 0.3. And since this is less than 0.5, we call this a nonpolar covalent bond. Now, what about the molecule F bonded to F? Well, this is pretty self-explanatory. These both have the exact same electronegativity. Fluorine, which is the largest electronegativity value on the periodic table, has an electronegativity of 4.0. And if you take 4.0, subtract 4.0, it equals 0. And that, by definition, is a purely nonpolar covalent bond. Now, finally, we take nitrogen and hydrogen. Nitrogen has a electronegativity of about 3.0, and hydrogen, as we just mentioned, has an electronegativity difference of 2.2. We did it up here. It doesn't change. It's the same electronegativity value no matter where it's bonded to. And since we subtract these, we get a difference of about 0.8. And since that's above 0.5, as we talked about before, this is a polar covalent bond. So this is something you'd be expected to know how to do. If I give you an electronegativity periodic table, you should be able to find the numbers, subtract them, and tell me whether it's polar or nonpolar, depending on if it's greater than 0.5 or less than 0.5. Well, that takes care of this video lesson. Thanks for watching.